So here's what we already know. We already know how to translate from ordinary language into propositional logic notation. In other words, we know what a simple statement looks like in propositional logic notation, and we know what a compound statement looks like in propositional logic notation. That is, we know that a simple statement is a statement that doesn't have any connectives, or we could say a simple statement is the smallest linguistic entity with a truth value. And a compound statement is a statement that contains at least one simple statement and at least one connective. Now we saw that there are 5 connectives: negation, conjunction, disjunction, conditional, and the biconditional. 4 of those 5 connectives, conjunction, disjunction, horseshoe, or conditional and biconditional, are connectives that join together in some way 2 sentences, while negation rejects whatever sentence it's in front of. We then looked at how we can construct truth tables to test out the possible truth values of compound statements by way of the truth definitions for each of the operators, tilde, dot, wedge, horseshoe, and triple bar, and how we can test out arguments as valid or invalid by way of truth tables. So what we get now is, in Chapter 8, a set of valid arguments, forms that we use as rules for deriving steps in a proof. So let's take a look at what we've got. First, we define natural deduction as a proof procedure by which the conclusion of an argument is validly derived from the premises through the use of rules of inference. We will see that some of these are already very familiar to you. You've been using them even if you haven't been aware of their formal names. We also can define a proof as a sequence of steps in which each step is either a premise or follows from earlier steps in the sequence. In other words, a step that follows from earlier steps would be considered an intermediate conclusion that is also a premise that leads us to the conclusion of the argument. Now, the rules of inference that we're going to use are implication rules. Replacement rules are rules of equivalence. We won't get to those in this class, but we've actually talked a little bit about them previously. So let me give you an example in the event that you're interested in what that looks like. But first, of course, I've got to plug in our handy dandy bamboo tablet and then wait for the computer to read it. Okay. So do you recall the phrase not either and, oops, I'm trying to make an equivalence here. Both are not. So it's not the case that either P or Q is truth functionally equivalent to the sentence, it's not P and it's not Q. So if you study the replacement rules, you'll see a whole slew of statements that are truth functionally equivalent to each other. And so in a proof, if you see one statement, you can replace it with its logical equivalence, or a logically equivalent statement. All right, but let's get started on what we're going to study. We have 4 rules in the first set and 4 in the second set. These are just divided out depending on which textbook you pick up. You'll get a slightly different arrangement, but typically these are divided out in order to kind of give you bite-sized pieces, if you will, rather than throwing all 8 of them at you at once, and in the most common occurrences. So Modus Ponens, Modus Tollens, Hypothetical Syllogism, and just Disjunctive Syllogism are the most common, arguably, of all of the implication rules. So let's start with our first set. So first, I want you to take a look at, I'm going to keep using our pen here. I want you to take a look at what is boxed up. This is the argument form known as affirming the antecedent or modus ponens. And it looks like this. If P, then Q, it is P, therefore Q. And as you can see from each of these two examples, the sentences in each of the premises as well as the conclusion can be really complicated. So what you want to make sure that you are comfortable with going into this material is the identification of the main connective. So the main operator, rather, for each of the sentences. So for example, the left side of the horseshoe is this dot sentence. That's the antecedent. And the right side of the horseshoe is this dot sentence. That's the consequent. So you have effectively P horseshoe Q. Then in premise 2, notice that the antecedent is affirmed, and then the consequent is, as a result, brought down, is inferred. Similarly, when you have the horseshoe in the second premise, you still have a modus ponens move, provided that the left side of the horseshoe, as is the case with premise 1, is affirmed. So it doesn't matter, again, how complicated the sentences are in the premises. It is still the case that when you have as the main operator horseshoe, you, when affirmed, pull down, when you affirm the antecedent, rather, you pull down the consequent. Notice a couple of examples of invalid applications. Now take a look at the invalid applications. And here I'm circling the left side of a disjunction. The main connective, the main operator, is a disjunction, and so you cannot pull down the right side of the horseshoe that is nested. In other words, before you could do anything with this horseshoe sentence, you would first have to dismantle this wedge. Remember, early on, I talked about this logic as a logic of assembling and disassembling statements at their joints. And this is an example of that. So if you don't, since the main joint of this statement is a disjunction, until you have dismantled it, you can't get to the horseshoe on the left side of that disjunction. And the same is also the case here, where we are attempting to simply, by affirming part of a complex sentence, pull down the right side of a disjunction. So here are a couple of examples from ordinary language. On the left in blue, you see the modus ponens form, and you have the following argument. If it's raining, then the streets are wet. It's raining, therefore the streets are wet. Compare that, well, actually contrast that with an imposter. So you have the same first premise in the red box, P horseshoe Q, but notice that the second premise is Q. When you affirm the consequent, you are not allowed to infer the antecedent. That's because this argument is invalid. Remember that we have our truth tables. So here's the first premise, here's the second premise, and here's the conclusion of the modus ponens argument. We know that the horseshoe is false when and only when the antecedent is true and the consequent is false. There are no operators to that are acting on each of these sentences. So we simply take the original referent values and plug them in. And you'll notice that on the two rows where the conclusion is false, there's at least one premise that's also false. On the other hand, when we take affirming the consequent, we end up with something else, which is at least one row, row 3, on which the conclusion is false while the premises are true. Since there's no other possible way for this argument to play out, we've exhausted the logical possibilities, and we've seen that this argument fails. Similarly, in terms of exhausting logical possibilities, with modus ponens, we see that there's no other way for this argument to play out, and since there's never a case where it fails, it's valid, and we use it as a rule of inference. Now let's look at modus tollens. Here again, on the in the blue box, you see the rule form, and you can notice that the consequent is denied, which yields a denial of the antecedent. You can think of an argument content as helping you to make sense of this. If I have 10 pennies, then I have 10 cents. I don't have 10 cents, therefore I don't have 10 pennies. If it is the case that you deny the consequent, what you're saying is that the necessary condition doesn't obtain, right? So if I have 10 pennies, then I have 10 cents, right? So our horseshoe here is the if-then relationship. Now, if I deny the 10 cents, I don't have 10 cents, then I can't possibly have 10 pennies. Remember that the consequent of the horseshoe is considered a necessary condition. What that means is, without this condition, when this condition is denied, the antecedent is also denied, right? So you would say, if I am alive, then I am breathing. I'm not breathing, therefore I'm not alive. Or if I'm alive, then my heart is beating. My heart is not beating, so I'm not alive, and so forth. Here again, we have a couple of examples of how this argument form plays out in rather complicated statements, right? So the main operator here is the horseshoe, and then the main operator in the second premise is the rejection of this parenthetical. So you can see how knowing your main operator is important to understanding how you can make sense of complicated statements and arguments. Same thing here. We have a complex antecedent, and then the simple statement C in the consequent is rejected, which yields a rejection of the antecedent. Here again, notice that on the invalid application, the error that is made is this disjunction hasn't yet been dealt with. Instead, this horseshoe sentence has just been effectively ripped off, right? So you can't work within a parenthetical using these rules of implication. You have to always deal first with the main operator. So you can see again that you have the contrast between the valid rule form and the imposter, in this case denying the antecedent. So you can construct a truth table for each so that you can see how the fallacy of denying the antecedent fails. It fails on row or line number 3. Next, we have what's called hypothetical syllogism. It's a syllogism because it is a 3-statement argument. In fact, all of these 3-statement arguments are syllogisms. They may just not be called that in terms of their formal name. And this is a hypothetical syllogism because it is constituted entirely by horseshoe statements, by hypothetical statements. So we have if P then Q, if Q then R, it follows that if P then R. Once again, take a moment to look at each of the valid applications, which is another way of saying look at how this rule can be manifested in rather complicated statements. And then see if you can determine how there are invalid applications below. So we have antecedent, consequent. The consequent of the first premise becomes the antecedent of the second, which then drops out in the conclusion. Horseshoe, horseshoe, horseshoe is the main operator in each. Notice here, again, we have the antecedent of premise 1 is the consequent of premise 2. That cancels out effectively. That transfers over effectively the horseshoe relationship to P wedge R, C wedge Q. Can you see how even though you have 2 horseshoes here in premises 1 and 2 of the invalid applications examples, you don't have consistent language. In other words, you don't have a repeated term as you do in your 2 valid applications. The same goes for the second example. Lastly, in this sequence is disjunctive syllogism, and I'm sure you remember this as well as the others from our discussion way back in chapter 1 of valid and invalid arguments. The disjunctive syllogism is valid because when you're presented with an either-or statement and you eliminate one side of the either-or statement, you're left with the other side. So you can say, I have pennies or quarters. I don't have pennies, so I must have quarters. Now take a look at the applications. And I think you can see that we have, once again, complex sentences, more complicated than what you're seeing in the rule form. But when you highlight the main operator for each, you see that we have a disjunction, and the left side of the disjunction is rejected, which leaves the right side. Disjunction or wedge, rejection of the left side of wedge, and so we're left with the right side. Now the invalid application here has to do with the fact that right now F is nested within a larger disjunctive sentence. So in order to get to what we want, we first need to dismantle the main operator wedge. All right, let's practice a little bit. First, identify the main operator in premise 1. Is it the wedge, the horseshoe, the dot, or the tilde? Well, remember our tips. First, your main operator is never going to be in a parenthetical. So that leaves out wedge, dot, and tilde. That means that horseshoe is the main operator. Another way to think about what the main operator is in terms of the scope of the operator. So what I mean by that is this. Take a look at the wedge. The wedge covers T and S. The dot covers P and tilde, and the tilde covers R. So the scope of these operators is fairly limited. On the other hand, the horseshoe brings both together by way of the meaning of horseshoe. Second premise is tilde parentheses P dot tilde R. In other words, it's not both P and not R. The tilde is the main operator, and that's because it governs the entire sentence. In other words, it's the only operator of the three operators that applies to the entire statement. It says no to both. Notice that the nested tilde, the one that's in front of R, only covers R, while dot covers P and not R. You should, at this point, when you look at line 3, be thinking about how rejecting the consequent of a conditional claim yields a rejection of the antecedent. So what I've got here is basically just a screenshot of one of your pages in the book, and I should have had the page out. Hold on. I'm grabbing my textbook because I hadn't done that when we started. Whoopsie. And I'm going to tell you where you can look. So we are under B, and strategies. Oh, maybe I'm wrong. Here we go. Sorry. Tactics and strategies for your first 4 rules are found on page 369. So, you can certainly look at these strategies. I think these are very helpful strategies. I think what is the most important strategy when you're given an argument and you're thinking about which rule would apply is to first look for the main operator in each of your premises, and then look for the relevant rule for that operator. So we'll employ the strategies that you're seeing here, as well as what I just mentioned, this very generic strategy, which involves identifying your main operator in each statement, and then looking at your rules for the relevant operators as we go into practicing, and that will be our next video. Okay, so let's try this together before we move on. And again, the practice that we're doing here is really limited. We practice separately in another video where we will be working through a number of derivations. So take a look at what you're given. You've got 4 premises, 1, 2, 3, 4, Q, L horseshoe, parentheses, C horseshoe, P, close parentheses, Q horseshoe, open parenthesis, R horseshoe, S close parenthesis, L, And then the conclusion is off to your right behind the slash. It's R horseshoe P. So if you're thinking about a conclusion, you want to generate a conclusion that's got a horseshoe in it, look at your rules and see which conclusion has as its main operator a horseshoe. It's one way for you to begin thinking about what you're going to do. In addition, look for the main operator in each of your premises. So 1 and 4 are premises that do not have any operators. They're simple statements. So you're not going to have to worry about looking for a main operator there. There is no operator. In 2 and 3, the main operator is the horseshoe that's outside of each of the parentheticals. So look at your rules. Is it the case that you have found your Modus Ponens rule that asks you to affirm or find an affirmation of the antecedent, that is the left side of horseshoe, in order to bring down the right side of the horseshoe? You'll also notice that Modus Tollens is a rule that involves horseshoe, but it's also a rule that involves a tilde, a negation, and so that's not going to apply here. So take a look at lines 1 and 3 and 2 and 4, and what you might want to do is pull them off to the side. So we have Q, Q horseshoe, S horseshoe P, right? We affirm the antecedent, we bring down the consequent, so we have S horseshoe P. And then we have L horseshoe S. Oh, I'm sorry, forgive me. I just wrote this out wrong. I mixed up lines 2 and 3. So it's Q, R, horseshoe S. You're probably screaming at your computer when you saw me make this mistake. Good for you. Okay, so your second premise is L horseshoe S horseshoe P. And then your fourth premise is L, and that yields, you've got your antecedent affirmed, and that yields S horseshoe P. Now let's put these two together, one on top of the other. We can do it in order if you want. R horseshoe S, S horseshoe P. What's the rule that allows you to yield by way of 2 horseshoes and a repeated term the antecedent of one horseshoe and the consequent of the other? That's hypothetical syllogism. And up here we have 2 Modus Ponens moves. What do you think? So number 5 is derived from 1 and 3. Now, did you have to use 1 and 3 first? No. You could have used 2 and 4 first if you wanted, but oftentimes it's easiest just to start with your first premise and ask what else looks familiar. So what else is consistent with that first premise? So that's why we did 1 and 3 first. Then 2 and 4 yield line 6. And then lastly, hypothetical syllogism by 5 and 6 yields line 7. So notice 2 things. We not only justify each inference with a rule name, we also cite the line number or numbers from which the derivation, from which the inference was made. So it's a really meticulous process of demonstrating the validity of an argument. So you're going step by step. Okay, now we've got 4 more rules. These are very common, but they're arguably not the most common of the valid argument forms. So for example, if you're planning on taking the law school admissions test, the LSAT, you most definitely want to be as armed as possible, but you could probably get away with just knowing the first four inference rules and how to employ them in order to do well on one of the sections of that exam. Anyway, constructive dilemma is effectively like a partial double modus ponens move. And what I mean by that is this. And I'm jumping ahead a little bit, but I think you'll get this. You know that dot is true when and only when each of the conjuncts is true. So that means if this statement is true, this one is true. So I've got P horseshoe Q as true. Now, if we assume that the left side of the disjunction is true, notice we've got one modus ponens. And then we have another one if we assume the right side of the disjunction. But notice here in premise 2, we're saying one or the other is true. Maybe both are true. We don't know, but at least one or the other is true. Therefore, one or the other of each of these consequents is true. Right? So affirm, affirm, infer, infer. Now, take a look at the example of the valid application. That's a mighty complicated statement. But remember, as long as you have identified your main operator, you won't have any trouble figuring out which rule is the appropriate rule to apply. And I think you can see that this is an imposter because here we've got a disjunction, not a dot. Simplification is a rule that we just talked about, right? We've been talking about this rule actually for a while. We know that dot is true when and only when each conjunct is true. So that means that if the dot is true, P is true. By the way, you could also pull down Q. In this version of the system, you pull down the left side of dot, and then later on when you get to equivalence rules, you could flip the P and the Q and then pull down Q. But just from a strictly truth functional standpoint, either one of these is legitimate to quote unquote pull down or infer. So here again, no matter how complicated the statement is, identify that main connective, that main operator, and you'll know what you can infer. Notice here again, since this dot is in a parenthetical, you can't simply rip out P from P dot Q because this is actually a disjunction. This is a P wedge Q, so you'd need to first reject one side in order to get the other side down, and then you'd have some work to do still if you could even get P. Then we have conjunction. It's just the reverse of simplification, right? If P is true, right? So in an argument, we assume the sentence is true. We assume this sentence is true. Therefore, both are true. And you can see that it doesn't matter if we're dealing with simple statements or pretty complicated statements, we can still conjoin them. And then lastly, addition. Now, you might remember being really frustrated by, or at least a little perplexed by, the fact that this argument is invalid. Right? So, on the other hand, we know that this argument form is valid. This is our disjunctive syllogism. So why am I talking about this when we're trying to talk about addition? Well, remember that we typically think of our disjunction in our ordinary ways of speaking about things. We think of our disjunction as exclusive. We take it to be it's one or the other but not both, right? You're in the library or you're in the coffee shop. And unless these two entities are in the same one in the same location, we assume you can't be in both, right? But logic doesn't know from what's not stated. So if you say one or the other, unless you specify but not both, it could be both. Now, why is that? Well, let's go back to our truth functionality of the wedge. Think about this statement as true. If P is true, then it's true that at least one or the other is the case, right? If I say Barack Obama is president, then it's true that Barack Obama or somebody else is president, right? As long as it's true that one of the disjuncts rephrase. As long as one of the disjuncts is true, the sentence as a whole could be true. And it doesn't matter whether the other side of the disjunct is true or is false. It could be either one. So go back to your disjunction definition, your wedge definition. You know that the wedge is false in one and one case only, and that's when each of the disjuncts is false. In all other cases, let me change the color for to highlight here. In all other cases, as long as one and maybe both are true, so as long as one is true, the statement as a whole is true, and in fact, both may be true. So we get to addition. A lot of people feel like the rule addition is cheating, like you're pulling something out of thin air, but it simply follows the very sort of loose requirements of the truth definition for the disjunction. I hope this introduction to the basics of natural deduction is helpful to you as you dive into the study of using inference rules to demonstrate the conclusion of a valid argument.